So let us recall what we did in the previous lecture. In the previous lecture, we have discussed regarding the compact matrix space. We have discussed the following results. So if X is compact, if and only if X is totally bounded, plus complete. Second result is every open covering has finite subcovering. That is known as Heinboer property. The third statement was if every sequence has convergent subsequence. The next statement we have discussed is if any family of subsets of X has finite intersection property, finite intersection property. Itself non-empty intersection. And the fifth statement is any subset, any infinite subset of X has a limit point. So we have proved the following results. In the last results I have given you as a project to do it. Now, in the next, we have discussed that if you have function f, which is a function from x to y, x is continuous and x is compact, then this will imply f of x is compact. So these are the results we have discussed into the previous lecture. Also, we have said that if the corollary of this statement that we have stated as if x is compact and f is a continuous map from x to y, then this fx is a closed plus bounded. And also we have discussed certain other results under which we have said that if you have function f, which is function from x to y, which is a continuous function, then certain preservation of this function is there. For example, if I give you convergence sequence in x, if I have a convergence sequence in x, let's say xn converges to x, then it will imply that f of xn will converge to f of x under the continuous map. That means under the continuous map, any convergence sequence is preserved. Convergence sequence will gives you a convergence sequence. The second thing we have observed that x is compact, then that will implies f of x is compact. That means under the continuous map, compactness is preserved. The other things we have discussed is x is open does not imply f of x is open. So under the continuous map, openness is not preserved. Closeness, same results we have for closed set. So closeness is also not preserved. To make this closeness and openness is preserved, you require your function has to be homeomorphism one. homeomorphic function. So f is homeomorphism from x to y, then this result is true. That is, x is open implies f of x is open. Now, other certain questions one can ask, that continuous function is preserves the conversion sequences. That means if you have the sequence which is converged in x, will implies that f of xn is convergent. What about Cauchy sequences? That means if I have a Cauchy sequence in x, will it be Cauchy in y? This is the first question. The second question I can ask is, if x is complete, can we say that f of x is also complete? And there are other same kind of questions you can ask by yourself and try to find out the answer for these questions. There are lots of questions you can ask here. That means some property which x has under the continuous map, whether the f of x has the same property. So these are the some questions you can ask by yourself and try to give the answer to these questions. Here I am talking about x is having the Cauchy sequence, then it does not implies that f of x has a Cauchy sequence under the continuous map. So for that, I am giving you this example. So this example says that the continuous image of a Cauchy sequence failed to be a Cauchy sequence. Continuous image of Cauchy sequence is failed to be a Cauchy sequence. That means under the continuous map, Cauchy sequence will not preserve. Okay. So for that, let us define x as 1, 1 by 2, 1 by 3, up to so on, with a discrete metric. And I am defining n, which we have a set of all natural numbers, 1, 2, 3, up to so on, with usual metric. That means any two elements if we pick here on n, then the distance between them is a difference of that. Now let us define this map f from x to n as f of 1 by n is equal to n. So any element of x is look like this. This is true for every n in n. Now why this function is continuous? Any argument for that you can give? Why this function f is continuous? We have seen that result that every function defined on a discrete metric, it's always continuous, because inverse image of any open set here, inverse image of, let's say G is in M, the inverse image will be in X, and every subsets of X is open. So that's why inverse image of any open set in M is open in X. So that's why we can say that we note that this F is continuous on X as X is a discrete metric. Metric space. Okay, because of it is discrete metric space, it is continuous. And we have already know that the sequence 1 upon n is Cauchy sequence in X. But the image f of 1 upon n, which is n, is not Cauchy sequence in X. Therefore, we have achieved the things that under the continuous map, the Cauchy sequence will not be preserved. Okay. The next example, which tells you that the continuous image of completeness or complete space need not be a complete. The continuous image of complete space need not be complete. To make it this is complete, or to have the example of this, the same example which we have discussed earlier will work. That means if we define a x with the 1, 1 by 2, 1 by 3 up to so on with a discrete metric. So with this you can take this as a discrete metric. And n is, you have a set of all natural numbers. Now we define f, which is from x to x comma, no, here it is you required a map from x to x itself. There is no requirement of n here. But this x is with the usual metric. So I just say that y will be 1, 1 by 2, 1 by 3 up to so on with usual metric. Or no need to write down this y also. I just write down the different manner. Define f from x to d. This capital D is a discrete metric which we have written here. It is a discrete metric D and it stands to small d, where d is equal to usual metric on x, as f of x is equal to x, and this is defined like this for every x in x. Now obviously this x is convergent because every discrete space is, well, obviously this x is complete because every discrete space is complete, and any map or define on a discrete metric space, then that map is continuous. So that's why this f is continuous and x is complete. But with usual metric, this sequence is actually converged to 0, which is not here in this x. So that means it is not complete. This side is not complete, but this side is complete. So let us give the argument of that. We note that f is continuous as x comma d is a discrete metric space. x comma and x comma d is also complete. But x comma small d is not complete. Therefore, we have the things that continuous image of a complete matrix space will not be a complete matrix space. Continuous image of complete matrix space need not be complete. So here in this lecture or in this till discussion, we have discussed that two things, that continuous image of Cauchy sequence will not be a Cauchy sequence. Continuous image of complete space will not be complete space. We have discussed that continuous image of a compact set will be a compact set. Means if X is compact, will stand to a compact set under the continuous map. For open set, it will not be true. For closed sets, it will not be true. So what are the such properties that continuous function or continuous function will preserve? The first preservation is the convergence. Continuous function will preserves the convergence. That means xn is convergent and f of xn is convergent. The second property that we have observed is compactness. Now it is up to you how many other properties you can establish and you can find out in that sense. Okay.